All right, Math 30-2, so we're going to look at some probability, mutually exclusive events, and the event A union B, or A or B. So in math, the event A or B, written as A union B, is said to occur if event A occurs, or if event B occurs, or if they both occur. Whereas A and B, or A intersect B, occurs if both event A and event B occur simultaneously. So we did that distinction in set theory in Unit 1. We're going to look at it again in probability. Investigating mutually exclusive events. Consider the experiment of rolling a die and noting the result. Let the event A be an even number is thrown, the event B being an odd number is thrown. Mark the outcomes of the experiment on the Venn diagram which represent the sample space. Alright, so A is an even number, 2, 4, 6. B is an odd, 1, 3, 5. List the outcomes for event A. Even numbers, 2, 4, 6 on a die. Event B, 1, 3, 5 on a die. The event A union B. So A or B is all the elements of the dice. And the event A intersect B, or A and B, well, can't have them both occur simultaneously. Let n at A represent the number of outcomes in event A, just like we had in set theory. So the number of elements in set A, there are 3 even numbers. Number of elements in set B, there are 3 odd numbers. Number of elements in A or B, well, there are 6 numbers on the die. Number of elements in A and B, there are no elements that are even and odd. Determine the following probabilities then. The probability of event A occurring. Well, we said there are 3 favorable, 3 even numbers out of a 6 total, or 1/2. B, there are 3 odd numbers out of 6, so that's 1/2. Probability of A union B occurring, A or B, well, 6 out of 6, or 1. And A intersect B, or A and B, would be 0 out of a 6, or no chance of that happening. So in this experiment, the events A and B have no common outcomes. The events A and B are called mutually exclusive, nothing in common. Notice that in the Venn diagram, the circle for A and the circle for B have no area of overlap. We say they are disjoint sets. Verify the following. The number of elements in A union B. We said there are 6 elements there. Number of elements in A is 3. Number of elements in B is 3. So 6 equals 6. Great, that's a verification. Probability of A union B. Well, we did that one right up here. That probability is 1. Probability of A, we said, was 1/2. And the probability of B was 1/2. Those are both right here. Probability of A, probability of B. So 1 equals 1. That's also a verification. Investigating non-mutually exclusive events. Consider the event of rolling a die and noting the result. Let event A be an even number is thrown. Event B be a multiple of 3 is thrown. Mark the outcomes of the experiment on the Venn diagram. So A is an even number. 2, 4. We'll put a 6 here because B is multiples of 3. 3 is not an even number, so it's going to stay in the B circle. 6 is an even number and a multiple of 3. 1 and 5 are neither even or multiples of 3, so they're going to be on the outside of the circles. List the outcomes for event A. Outcomes for event A are still 2, 4, and 6. Outcomes for event B are now 3 and 6. Outcomes for event A union B are all the things in the circle. 2, 3 in the circles together, 2, 3, 4, 6. A intersect B, or A and B, is the element 6. So again, complete the following. How many elements are in A? We've got 3 even numbers. How many elements in B? 2 multiples of 6. A union B, there are 4 elements there, and A intersect B, only the number 6. There is one element there. So determine the probabilities. Probability of A, 3 out of 6, still a half. Probability of B, 2 out of 6, so that makes a third. Probability of A union B, well, there's 4 elements out of 6, or 2/3. And probability of A intersect B, there's 1/6 chance of that happening. In this experiment, the events A and B have a common outcome. So they now have a common outcome, so they are not mutually exclusive. That number 6 is common to both even and multiples of 3. Notice the Venn diagram, the circle A and B have an overlap area. This represents A and B. Sets A and B are not disjoint. Verify the following. Number of elements in A union B, if we look up to part C right here, number of elements in A union B is 4. Number of elements in A is 3. Number of elements in B was 2. Minus number of elements in A intersect B, which was 1. So 4 should equal 3 plus 2 minus 1. And that does equal 5 minus 1. So that's great. Probability, let's look at part D. Probability of A union B is 2/3. Probability of A we said is 1/2. Probability of B we said is 1/3. Minus the probability of A intersect B, which is 1/6. So if you want to make these all a common denominator and go ahead and work this out, so 4/6 is going to equal 3/6 add 2/6 minus 1/6. And you see that that also works out. Events are said to be mutually exclusive if they have no common outcomes. Two events A and B are mutually exclusive if the probability of A intersect B is 0. Don't forget that. All right. All right, if you look at the probability of event A union B, so you use the information below to work out events of union, A union B. If the events are mutually exclusive, we're going to use this formula. If the events are not mutually exclusive, we're going to use this formula. Both these formulas are in your on your formula sheet, and they'll be given to you on the diploma. So the big difference to know is which one's mutually exclusive and which one's not. Example 1 then, in each case state whether the events A and B are mutually exclusive or not. So we have to decide. A, the experiments, a die is rolled. Event A is an even number, event B is an odd number. Are these mutually exclusive or not? These are mutually exclusive. All right. You can't have an even number and an odd number occur at the same time. Part B, a card is drawn from a standard deck. Event A is a face card. Event B is a club. Are they mutually exclusive or not? No, they are not mutually exclusive. Reason why? Well, you can have a face card that's a club. You can have the king or queen or jack of clubs. And that would satisfy a face card and a club, so they're not mutually exclusive. C, 2 dice are thrown. Event A is the dice shows the same value. Event B, the total score is 11. Are they mutually exclusive? Can dice that show the same score ever add up to 11? No, they can't. So we would say that these events are mutually exclusive. Notice that the mutually exclusive events in A, an even number occurs, and an odd number occurs, are also complementary. Complementary events will always be mutually exclusive because they have no outcomes in common. Example 2 then, consider the experiment of drawing a card from a standard deck. The following events are defined. Event A is a face card, event B is a red card, C is a club, D is an ace, and E is a black card. Which pairs of events are mutually exclusive? So mutually exclusive events, which pairs? Event A is a face card and event D is an ace. So face cards and aces can't happen at the same time. They're mutually exclusive. You can have a red face card or a club face card or a black face card. So only A is mutually exclusive with D. If you go to B, a red card and a club. Well, you can't have a red card and a club, so B and C are mutually exclusive. A red card and ace, B and D. Yes, you can have a red ace. And what about B and E, a red card and a black card? No, you can't have both those. You can't have a red card and a black card at the same time. C, a club. You have an ace of clubs and the club is black, so C isn't mutually exclusive with D or E, and D and E, you can have an ace that's a black card. So those are the only three mutually exclusive events. Of these pairs, which of these are complementary? Complementary meaning exact opposite. So we'd say a red card and a black card selected. Complementary events for this one, B and E. All right. All right, let's look at example 3. Events have been represented on a Venn diagram. State all the pairs of events that are mutually exclusive. Event A does not overlap with event B, so they must be mutually exclusive. Event A does not overlap with C, they must be mutually exclusive. And event A does not overlap with D, so they must be mutually exclusive. B overlaps with C and C overlaps with D. However, B and D do not overlap, so they must be mutually exclusive. All right. Example 4. Use the given information and the probability formula to determine whether the events A and B are mutually exclusive. So if you go look up at the probability formula on the previous page, probability of A union B, if they are mutually exclusive, will be probability of A plus the probability of B. That's the formula for mutually exclusive. That was back on page 139. That's on your formula sheet. Well, let's see if these two events are mutually exclusive. Probability of A union B is 7/12. Probability of A is 1/4. Probability of B is 1/3. Does 7/12 equal 1/4 plus 1/3? Well, if you remember how to add fractions to get a common denominator, 1/4 is the same as 3/12. 1/3 is the same as 4/12. We can see that 7/12 is the same as 3/12 plus 4/12. So yes, the events A and B are mutually exclusive. All right. Example 5. A card is drawn from center deck of 52. Use formulas to determine the probability that a 9 of diamonds or a heart is drawn. All right, let's look at that. So the first thing we have to decide is whether 9 of diamonds or a heart is drawn. Are these mutually exclusive? Can you have a 9 of diamonds and a heart at the same time? No, so these are mutually exclusive events. So let's use the proper formula. Probability of a 9 of diamonds or the probability of a heart. All right, so 9 of diamonds and a heart should be the probability of 9 of diamonds plus the probability of a heart. All right, so the probability of a 9 of diamonds, well, there's only one 9 of diamonds in the deck out of 52 cards. The probability of a heart, there are 13 hearts in the deck out of 52 cards. So the probability of a 9 of diamonds unioned with a heart would be 14 out of 52. Or in lowest terms, we'd say 7 out of 26. All right. Event B, let's look at part B. A 9 or a heart is drawn. Are these mutually exclusive? No, these are not mutually exclusive. So if they're not mutually exclusive, we have to use that other formula. Probability of a 9 union with a heart would be the probability of a 9 plus the probability of a heart minus the probability of a 9 and a heart. 9 and a heart. All right, so the probability of a 9, well, there are 4 9s in the deck out of 52. The probability of a heart, there are 13 hearts in the deck out of 52. Minus the probability of a 9 and a heart, well, there's only one 9 of hearts. That's 1 out of 52. So that probability would be 17 minus 1, which is 16 out of 52. Or in lowest terms, 4/13. All right. All right, let's look at example 6. Blocks of different shapes and colors are placed into a bag. There are 3 cubes, 1 red, 1 blue, 1 green, 2 pyramids, 1 red and yellow, and 5 cylinders, 1 blue, 1 yellow, and 3 red. So, A, determine the probability that a block selected at random will be a pyramid or a cube. First off, you have to decide, is this mutually exclusive or not? Can you pull a pyramid and a cube out at the same time? No. So yes, these are mutually exclusive. Nice. That's the formula we want to use. Probability of a pyramid or a cube. Mutually exclusive events will be probability of a pyramid plus the probability of a cube. All right. So we see that there are 2 pyramids. Out of how many shapes are in the bag? 10. Plus there are 5 cylinders out of 10 shapes in the bag. However, we don't want a cylinder, we want a cube. Sorry. There are 3 cubes out of 10. So 2 pyramids, 3 cubes, we've got 5 shapes out of 10. So that's a probability of 1 out of 2 choosing a pyramid or a cube. Part B, what's the probability that the item will not be red? Well, this isn't really mutually exclusive or not. There are 10 objects, and how many are red? Probability not red. Or we could say it like this. Not red. Well, if you look, there are 1 blue, 1 green, 1 yellow, another blue, another yellow. That's 5. 5 out of 10. So again, a 1 out of 2 chance of the item chosen not being red. And finally C, what's the probability that the block selected at random will be red or a cylinder? Are these mutually exclusive? Are there any red cylinders? Yeah, there are 3 red cylinders. So this is not mutually exclusive. So we must use the correct formula. So probability of red union with a cylinder should be probability red plus the probability of a cylinder minus the probability of a red union cylinder. All right. So the probability of red we just determined was 5 out of 10. Probability of a cylinder is also 5 cylinders out of 10. Minus the probability of a red cylinder. Well, there are 3 red cylinders out of 10 objects. So we add that up. 5, 10 minus 3 is 7 tenths. All right. All right, last example. Let's look at number 7. Tom and Andrew were asked to solve the following problem. 200 people with neurology symptoms, which included headaches and backaches, participated in a study to evaluate a pain relief medicine. All the people took the medicine, and the results were as follows. 60 people experienced headache relief, 126 experienced backache relief, and 36 experienced relief from both. Right there, 36 people experienced relief from both. Is this a mutually exclusive or a not mutually exclusive event? Well, we'd have to say that these are not mutually exclusive. All right. Headache and backache, well, you can experience both and get relief from both. What's the probability that a person who takes a drug experiences relief from at least one of the 2 symptoms? And part 2, neither of the symptoms. Tom decided to solve the problem using probability formula. So we decided it's not mutually exclusive. We're going to use the correct formula for that then. Let's complete his work. The probability for probability for headache relief was 60 out of 200 or 0.3. The probability for backache relief then should be 126 out of 200, which if you put that in lowest terms is 0.63 as a decimal. And both probability of headache and backache relief 36 experienced relief from both. So 36 out of 200, which is 0.18. Great. Now if we do part 1, at least one of the two symptoms. What's the probability that you're going to have relief from at least one of the two? So that's the probability of headache or backache. They are not mutually exclusive. So that should be the formula: probability of a headache plus the probability of relief from the backache minus the probability from the headache and the backache. All right, both. So we'll substitute in. The probability of relief from the headache is 0.3, relief from the backache is 0.63, and relief from both is 0.18. All right, so if you work that out, we come up with 0.93 minus 0.875. Great. If we look at event 2, what's the probability that the person experiences relief from neither of the symptoms? Well, if this is 0.75 is relief from one or the other, we would just say 1 minus that. All right. Probability from neither of the symptoms, 0.25. So those are complementary events. Have to add up to 100%. Andrew decided to solve the problem using a Venn diagram. Complete the Venn diagram to determine the answer to the problem. So we were told 36 people experienced relief from both. We're going to put that in the middle. We were told that 60 people experienced relief from headaches. So 60 minus 36 is 24. That's going to go in the headache circle only. We were told that 126 people experienced backache relief. Already 36 in the backache relief, so 126 minus 36 is 90. Now let's answer the question. Part 1, probability of headache or backache relief. Well, if you add all that up, 24 plus 36 plus 90, all the ones in the circle out of 200. All right. All the ones in the circle at 200 would be 0.75. Part 2, probability of neither. Well, that's the number of people outside the circle. So if you add 24 and 36 and 90, we came up with 150 out of 200 over here. So that means there's 50 people outside the circle. So 50 people out of the 200, which is 0.25. All right, so we get the same answers. Great, you guys have your assignment. Let's get after it.